These are 12 engineering systems that keep America's aircraft carriers stable in the most violent storms on Earth, when 100,000-ton floating cities face winds over 100 miles per hour and waves that tower 6 stories high. When Typhoon Cobra slammed into the U.S. Third Fleet in December 1944, 3 destroyers capsized and sank within hours. Nearly 800 sailors died. 5 aircraft carriers suffered serious damage, with one ship tilting to a terrifying 45-degree angle. But here is what is remarkable. None of those carriers actually sank. Today's nuclear-powered supercarriers are engineered to be virtually unsinkable, even when nature unleashes its full fury. The secret lies in 12 interconnected systems that work together like a perfectly orchestrated defense against the sea itself. Let me show you exactly how these floating fortresses stay afloat when physics says they should sink. Type proud in the comment section below if you think that U.S. aircraft carriers are the best in the world. First, the hull design tricks your eyes. When you see a carrier from the side, it looks like it tapers to a knife edge that cuts through water. That's pure illusion. The narrowing only extends to the waterline, designed purely to reduce surface drag. Pull that ship into dry dock, and you'll discover the truth beneath the waves. Below the waterline, carriers have a wide, flat bottom that creates an incredibly stable platform. Think of it like an iceberg in reverse. The narrow part you see, the massive, stable base you don't. This hull shape creates what naval architects call metacentric stability. The center of buoyancy sits higher than the center of gravity. When a carrier tilts in heavy seas, this creates a powerful righting force that actually grows stronger the farther the ship leans. It's like a weighted toy that always rights itself, except this toy weighs more than 15,000 elephants. Nimitz-class carriers stretch 1,092 feet long with a beam of 252 feet overall, but only 134 feet at the waterline. That means the flight deck dramatically overhangs the hull below, and this isn't an accident. Naval architects deliberately shift the island superstructure to the starboard side, then balance this by extending the port side of the flight deck. This creates perfect equilibrium while keeping the full deck clear for aircraft operations. The real genius lies hidden inside the hull, the watertight compartment system. Modern carriers contain several hundred watertight compartments spread across all decks. These are not just rooms with doors. They are independent survival pods separated by steel bulkheads that extend from the keel to the main deck. If a torpedo punches through the outer hull or massive waves breach the flight deck, the flooding stops at the nearest bulkhead. The ship might take on thousands of tons of water in one compartment and barely list. During World War II, the carrier Monterey caught fire during Typhoon Cobra. Aircraft on the hangar deck slammed into one another like pinballs, as one crew member later recalled. That crew member was future President Gerald Ford. Captain Stuart Ingersoll was ordered to abandon ship, but he refused. Ford and hundreds of sailors fought the fires compartment by compartment, and the watertight system prevented flooding from finishing what the typhoon started. The Monterey survived. Modern carriers take this protection even further with double-bottom construction. Imagine a ship within a ship, 2 complete layers of steel plating separated by a gap. If the outer hull gets punctured, the inner hull maintains watertight integrity. It is like having a spare tire for your entire ship. Then there's the ballast system, thousands of tons of adjustable weight that can shift in minutes. When hurricane-force winds try to push a carrier over, computers automatically flood or empty ballast tanks throughout the ship. This moves the center of gravity precisely where it needs to be to counteract the tilting force. The ship essentially adjusts its own balance in real time. Weight distribution follows the same principle as a well-designed skyscraper. All the heaviest components, nuclear reactors, machinery, fuel, and ammunition, sit as low as possible in the hull. The flight deck and superstructure above are deliberately kept light. This creates an extremely low center of gravity that resists capsizing. Active stabilization systems add another layer of protection. These computer-controlled fins extend from the hull underwater and automatically adjust their angle based on wave action detected by gyroscopes. When sensors detect the ship starting to roll to port, the starboard fin immediately adjusts to create a hydrodynamic force that pushes back. It is like having invisible hands constantly steadying the ship. Bilge keels provide passive stability without any moving parts. These long steel projections run along the bottom of the hull and act like underwater brake pads. As the ship tries to roll, water flowing around these keels creates resistance that dampens the motion. Modern anti-roll systems can reduce rolling by 80 to 90%, even in severe seas. The propulsion system itself contributes to stability. 4 massive bronze propellers, each 25 feet in diameter and weighing 66,000 pounds, can generate 260,000 shaft horsepower. But it is not just about speed. These propellers create directed water flow that helps maintain heading in crosswinds and provides additional directional control when waves try to push the ship around. Nuclear power eliminates a critical vulnerability that sank those destroyers in 1944. Those ships ran low on fuel, which made them top-heavy and unstable. Nuclear carriers never face this problem. With virtually unlimited range and 20-year reactor cores, they maintain consistent weight distribution throughout their deployment. In 2021, USS Gerald R. Ford underwent full ship shock trials, controlled explosions designed to simulate battle damage in extreme conditions. The Navy detonated 40,000 pounds of ordnance right off the ship's beam, creating a blast that registered as a magnitude 3.9 earthquake. Captain Paul Lanzalotta reported afterward that they had 0 catastrophic failures, 0 flooding situations, and 0 fires. But even with all this engineering, carriers still respect the sea. During Hurricane Sandy in 2012, Norfolk Naval Base evacuated multiple carriers to deeper water where they could ride out the storm safely. The ships did not leave because they could not handle the weather. They left because hurricanes can drive storm surge and debris into port facilities, creating hazards that even the most advanced protections cannot eliminate. The latest Gerald R. Ford class carriers push these systems even further. At 1,106 feet long, with 4.5 acres of flight deck, Ford displaces over 100,000 tons, but requires 700 fewer crew members than Nimitz-class ships thanks to automation. These systems monitor and adjust stability parameters continuously, making thousands of micro-adjustments that human crews could never match. Every system I've described works together like a mechanical symphony. When 70-foot waves crash over the bow and winds of 120 miles per hour try to flip a floating city, 12 different engineering marvels activate simultaneously. Hull shape provides inherent stability. Compartments prevent catastrophic flooding. Ballast systems shift weight. Stabilizers counteract wave motion. Nuclear power maintains consistent mass distribution. Computer systems coordinate it all. The result is a platform so stable that flight operations can continue in conditions that would ground aircraft on land. While merchant ships run for port and smaller warships get tossed like toys, aircraft carriers maintain course and mission capability. This is why America's carrier fleet has never lost a single ship to weather in over 50 years of global operations. When you combine centuries of naval architecture with nuclear power, advanced materials, and computer control systems, you create something that doesn't just survive the ocean, it masters it. The engineering isn't just remarkable, it's the difference between America projecting power anywhere on Earth or watching helplessly while nature proves that in the battle between human engineering and the sea, the better design wins every time.